Each segment of an electrical distribution system is designed and sized to accommodate its specific loads, rather than being solely dependent on the size of the upstream transformer. The transformer's main function is to step down or step up the voltage to the required level for the downstream loads. The size of the transformer, measured in kilovolt amperes or kVA, is determined by the total load demand of these downstream circuits, which often include multiple subpanels. Electrical feeders, which are the conductors carrying electricity from the main distribution panel, or MDP, to the subpanels, are sized to handle the specific loads connected to each subpanel. This sizing process involves calculating the expected current draw of each load and selecting conductors with an ampacity rating sufficient to carry that current safely, in accordance with the National Electrical Code, or NEC. In scenarios where the original feeders from the MDP to the subpanels were sized based on the loads present at the time of installation, and those loads have not increased significantly, the existing feeders are generally still adequately sized to handle the current demand even after installing a new transformer. To determine the correct feeder size, several factors need to be considered. Firstly, the continuous load on the feeder should be calculated. According to the NEC, feeders must be sized to carry not less than 125% of the continuous load. This means that if a feeder supplies a continuous load of, say, 80 amps, the feeder must have an ampacity of at least 100 amps. Secondly, the non-continuous load must be added to the result of the continuous load calculation. The sum of these two values represents the total calculated load in the feeder. Thirdly, the appropriate conductor size is selected based on its ampacity rating. NEC Table 310.15. V16 provides ampacity ratings for various conductor sizes and insulation types. It's important to choose a conductor with an ampacity that is equal to or greater than the total calculated load. Fourthly, voltage drop should be considered. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop on feeders to no more than 3%. Calculations for voltage drop depend on the length of the feeder, the conductor size, and the current flowing through it. If the voltage drop exceeds the recommended limit, a larger conductor size may be necessary. Fifthly, the overcurrent protection device, such as a circuit breaker or fuse, must be sized to protect the feeder from overloads and short circuits. The NEC provides guidelines for selecting the appropriate overcurrent protection device based on the conductor ampacity. It's essential to ensure that the overcurrent protection device does not exceed the conductor's ampacity rating. Finally, the installation methods and ambient temperature need to be taken into account. The ampacity ratings in NEC Table 310.15. V16 are based on specific installation conditions and ambient temperatures. If the actual installation conditions differ, such as conductors bundled together or exposed to high ambient temperatures, the ampacity of the conductors may need to be derated. In certain situations, exceptions to this general rule may apply. Firstly, if the original transformer was significantly overloaded, the new transformer may necessitate increasing the feeder sizes to ensure proper operation. In such cases, the existing feeders may have been operating close to their maximum capacity, and the increased capacity of the new transformer could potentially overload them. Secondly, if the load characteristics have changed drastically, for example, from a primarily resistive load to a heavily inductive load, the feeders may need to be reevaluated for their suitability. Inductive loads, such as motors, can draw significantly higher current during startup, which could potentially overload the feeders. However, in most common scenarios, the size of the electrical feeders from the MDP to the subpanels is not directly affected by the size of the transformer. As an example, consider a building with a 300 kVA transformer and feeder size for the loads at the time of installation. If a new 225 kVA transformer is installed, and the loads have not increased, the existing feeders should still be adequate. However, if the building's load has increased significantly, or if the load characteristics have changed, it's important to reevaluate the feeder sizes to ensure they can handle the new demand. It is crucial to perform load calculations to determine the actual current demand of the subpanels. This involves summing up the loads of all the equipment connected to each subpanel and applying any applicable demand factors. Demand factors are used to account for the fact that not all equipment will be operating at its maximum load simultaneously. Once the load calculations are complete, the feeder sizes can be compared to the calculated loads to ensure they are adequately sized. If the load calculations indicate that the existing feeders are undersized, they will need to be replaced with larger conductors. It's also important to consider any future load growth when sizing feeders. If there is a possibility that the load on the subpanels will increase in the future, it's a good idea to size the feeders accordingly to avoid having to replace them again later. The NEC provides guidelines for sizing feeders based on the expected future load. In addition to the above considerations, it's important to follow all applicable codes and regulations when sizing electrical feeders. The NEC provides detailed requirements for conductor ampacity, overcurrent protection, and other aspects of feeder design and installation. It's also important to consult with a qualified electrical engineer or contractor to ensure that the feeders are properly sized and installed. Selecting the right size conductors for electrical feeders is crucial for safety and reliability. Undersized conductors can overheat, leading to insulation damage and potentially causing fires. Oversized conductors can be more expensive and difficult to install. By following the guidelines outlined above and consulting with a qualified professional, it's possible to select the appropriate conductor sizes for any electrical feeder application. To elaborate on the practical application of these concepts, let's consider a hypothetical scenario. Imagine a commercial building with several subpanels, each serving different areas of the building, such as lighting, HVAC, and office equipment. The original electrical system was designed with a 300 kVA transformer and feeders sized to accommodate the loads at the time. Over the years, the building's occupancy and usage patterns have changed. Some tenants have moved out and new tenants have moved in with different electrical requirements. As a result, the overall load on the electrical system has decreased. The building owner decides to replace the existing 300 kVA transformer with a new 225 kVA transformer to better match the current load demand. Before installing the new transformer, the building owner hires an electrical engineer to assess the existing electrical system and determine whether the feeders from the NTP to the subpanels are still adequately sized. The electrical engineer begins by performing load calculations for each subpanel. This involves reviewing the connected loads, applying demand factors, and calculating the total current demand. The engineer finds that the loads on some subpanels have decreased significantly, while the loads on others have remained relatively the same. The engineer compares the calculated loads to the ampacity ratings of the existing feeders. The engineer discovers that the feeders serving the subpanels with decreased loads are now significantly oversized. However, the feeders serving the subpanels with relatively constant loads are still adequately sized. Based on these findings, the electrical engineer recommends that the building owner replace the oversized feeders with smaller conductors. This will not only reduce the cost of the electrical system, but also improve its efficiency and safety. The electrical engineer also recommends that the building owner install new overcurrent protection devices that are appropriately sized for the new feeders. By following these recommendations, the building owner can ensure that the electrical system is properly sized and operates safely and efficiently. The new 225 kVA transformer will be able to handle the current load demand without overloading, and the feeders will be adequately sized to carry the current to the subpanels. In addition to the above scenario, it's important to consider the impact of harmonic currents on feeder sizing. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as computers, LED lighting, and variable frequency drives. These harmonic currents can cause additional heating in conductors and transformers, which can lead to premature failure. To mitigate the effects of harmonic currents, it's important to use conductors that are rated for harmonic current loading. These conductors have a higher ampacity rating than standard conductors and are designed to withstand the additional heating caused by harmonic currents. It's also important to use transformers that are designed to handle harmonic currents. These transformers have a higher K-factor rating, which indicates their ability to withstand harmonic current loading. In summary, when sizing electrical feeders, it's important to consider all of the relevant factors, including the continuous load, non-continuous load, voltage drop, overcurrent protection, installation methods, ambient temperature, future load growth, and harmonic currents. By following the guidelines outlined above and consulting with a qualified professional, it's possible to select the appropriate conductor sizes for any electrical feeder application and ensure the safety and reliability of the electrical system. The National Electrical Code, or NEC, is a comprehensive set of standards that governs the safe installation of electrical wiring and equipment in the United States. It is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. The NEC contains numerous articles and tables that provide guidance on various aspects of electrical design and installation, including feeder sizing. Article 215 of the NEC covers feeders, which are defined as the circuit conductors between the service equipment, or the source of a separately derived system, and the final branch circuit overcurrent device. This article provides requirements for feeder ampacity, overcurrent protection, voltage drop, and other important considerations. Table 310.15. B16, formerly known as Table 310.16, is one of the most frequently used tables in the NEC for determining the ampacity of conductors. This table provides ampacity ratings for various conductor sizes and insulation types, based on specific installation conditions and ambient temperatures. The ampacity ratings in Table 310.15 B16 are based on the assumption that the conductors are installed in free air and are not subject to excessive heat or bundling. If the conductors are installed in a conduit or cable, or if they are subject to high ambient temperatures, the ampacity ratings must be derated accordingly. The NEC also provides requirements for calculating voltage drop in feeders. Voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop on feeders to no more than 3%. To calculate voltage drop, the following formula can be used. Voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, which is approximately 12.9 ohms for copper conductors and 21.2 ohms for aluminum conductors. A is the current in amps, D is the one-way distance of the feeder in feet, and Cm is the circular mils of the conductor. The NEC also provides requirements for overcurrent protection of feeders. Overcurrent protection devices, such as circuit breakers or fuses, are designed to protect conductors from overloads and short circuits. The NEC specifies the maximum allowable overcurrent protection for various conductor sizes and insulation types. It's important to select an overcurrent protection device that is properly sized to protect the feeder without causing nuisance tripping. In addition to the above requirements, the NEC also contains provisions for specific types of feeders, such as those serving motors, HVAC equipment, and emergency systems. These provisions provide additional guidance on sizing and protective feeders in these specialized applications. When sizing electrical feeders, it's essential to consult the NEC and follow all applicable requirements. The NEC is a complex and comprehensive document, and it's important to have a thorough understanding of its provisions before attempting to design or install electrical wiring. It's also advisable to consult with a qualified electrical engineer or contractor to ensure that the feeders are properly sized and installed in accordance with the NEC. Proper feeder sizing is critical for the safe and reliable operation of electrical systems. Undersized feeders can overheat, leading to insulation damage and potentially causing fires. Oversized feeders can be more expensive and difficult to install. By following the NEC requirements and consulting with a qualified professional, it's possible to select the appropriate conductor sizes for any electrical feeder application and ensure the safety and reliability of the electrical system.